Okay, so today, I kind of alluded to this a little bit earlier. Today, this is maybe one of the most important lessons I'm going to give. So that's one of the reasons why I really want to make sure I make my YouTube video, because I think this will be worth rewatching again. Maybe not even just this year, but next year. If you guys take Science 10 and then Chemistry 20 and Chemistry 30, this is really the foundation upon which everything gets built. You have to know your periodic table. I'm going to give an analogy here. I've talked about my kids before with you guys, right? So I've got a 6-year-old, she's Kinsey, a 4-year-old, Cami, and a 1.5-year-old is Cadence. And so Kinsey is in grade 1, and what she's learning how to do right now is learning how to read. And Cameron is in preschool, and she's kind of also learning how to read, but she's at a different stage. Cami being 4 right now, our goal with her is to teach her letters, letter recognition. And so if I were to tell her, Cami, what is this letter right here? Hopefully she can say, that's a K, right? And sometimes she's good at it, and sometimes she's not, right? Like, if I give her a P, sometimes she thinks it's a B or a Q, you know what I mean? Like, sometimes they get them, like, backwards, right? Whereas Kinsey's at a different stage. Kinsey not only knows how to look at her letters and identify them, but she can start reading words. She knows, like, this is pig, and this is big, and she gets, like, rhyming parts to it, right? And she's starting to work on sentences. The reason why I want to bring their reading up is that, to me, that's how we need to learn chemistry. We need to learn how to speak the language of chemistry. So that if I one day tell you that we take calcium chloride and add it to rubidium oxalate, you know what I just said. Because I'm guessing right now, calcium chloride, rubidium oxalate, you may not even, like, what language is that? Right? I need you to be able to eventually, not right now, but eventually be able to, just like my older daughter can do. If I say, Kinsey, how do you spell pig? Not only can she spell pig, but she even gets that the word pig means this pink, fat creature that, like, rolls around in the mud that tastes like bacon, right? Like, she needs to be able to make that a mental association as well. When I said rubidium oxalate, what did your mind think of? Do you know what rubidium oxalate is? I doubt it, which is fine. I don't expect you to, right? But my goal is that as I teach you more and more chemistry, one day, like, I am able to immediately picture what rubidium oxalate is. I know that rubidium oxalate will be RbOOCCOO, just because I happen to know that. I wouldn't have expected you guys to know that. Actually, it would have been Rb2OOCCOO. Anyways. Back to my analogy then. When we start with the periodic table is literally like the building blocks of what we're going to learn. It's like our letters. Before we can put letters into words and words into sentences and make that association between this word means this object, we need to start like my 4-year-old is learning. I need to teach you guys your letters. Does that make sense? Eventually, we're going to put our letters together. So, like, to give you an example of where we're going long term. Today we're going to learn about something like, say, Na. Na is sodium. And we're going to talk about it just as a letter all by itself. Or H. H is hydrogen, it's a letter. And just like I give my 4-year-old flashcards and say, hey, what does Na stand for, or what does H stand for? And she has to, like, be able to say, like, the letters. I need you guys to know that this is sodium and this is hydrogen. Right? And eventually you'll have some of them memorized, like whatever W is. It's tungsten. Right? Now, I have that memorized because, like, I've learned chemistry a lot, right? I don't expect you to know that yet, but we got to get to that point. Now, when you first start learning chemistry, we're going to give you a periodic table. Okay, like, there is no expectation that you need to have these things memorized. But does that make sense for step 1? First, we got to learn all of these letters on the table. Maybe not memorize them, but, like, know how they work. Later, what we're going to learn how to do is make compounds. Like, for example, NaCl. We're going to put 2 of them together. And we need to know how to name that. This would be like a word. Or maybe I'd give you a compound like NaCH3COO. We're not ready to do this anytime soon, but at one point, I need you guys to be able to tell me, well, what do you call this thing? Just like for my daughter, she now knows that this says big. I need you guys to know what this word means. But more than that, not only do I need to know you to know, like, what to call this, I need you to know, like, what does it look like? What does it mean when you see this? Just like if she can say the word big, but she doesn't know what the word big means, like if she thinks big means this is a big, well, like that's not helpful either, right? Like you have to know that big refers to something that's like large and growing, right? So not only do you need to know what to call it, but we have to have an idea of, well, like, what does it look like? What are its properties? And then finally, we need to get you to the point where you're writing sentences. And so one of my goals, and we will do this before we're done our time together in Science 9, is be able to write a sentence like this. CaCl2 plus NaOH turns into CaOH2 plus NaCl with a 2 in front of it right there. And at some point in the next couple of weeks, I'm hoping that you guys will be able to look at this and like it'll mean more to you than it does right now. Because I'm guessing right now when you look at that, you go, what? But like, how is that different though than my 6-year-old? If I were to hand her a book of Shakespeare and tell her to read it, she's not ready to read Shakespeare yet. Like that's challenging stuff to read. Not only to read the words, but to interpret and to understand. You get what I'm saying? That's where you guys are at. You guys right now are like my 4-year-old. We got to start at the beginning with our letters, and eventually we want to be able to look at something like this and not have it look like gibberish. Because like I said, right now it probably looks like gibberish to you. You're like, I know a little bit. Like maybe you know, hey, this O right here is oxygen. Hey, you're not wrong. That O there is oxygen, right? Perfect. H is hydrogen. That's our goal. So anyways, let me go back to this slide here. Let's start at the beginning then. Our goal today then is to talk about the periodic table. So a bit of history, I've already mentioned this. Dmitry Mendeleev is the guy who we credit with kind of developing the periodic table. And it's actually not that long ago in the grand scheme of things. We're talking 150 years ago. Which, in like the big history of chemistry and physics, like when we did our lesson on like history, we talked like thousands of years ago. This is actually pretty recent. Okay. What he did is he arranged all of the known elements and he put them into columns and rows. My goal today, one of my many goals, is to explain how these columns and how these rows kind of work, what the logic was to his table. Because let me see if I can explain this. When he made his table, he could have made the table be like a 4 by 5 table, or he could have made it 2 by 10. 4 by 5 would be like, say, 20, right? And 2 by 10 would also be 20. I need to try to explain to you why we have our table in the pattern we did. Why are there 7 rows? Why are there 18 columns? Why not 6 and 12? Why not 14 and 1, right? Like, what's that rationale? So the first thing I need you guys to know is that the modern periodic table, although it's arranged in rows and columns, it's based on something called an atomic number. This is the first definition I need you guys to know, atomic number. I would like for you guys to try to find in the top corner of the table in front of you, and I'm sorry that it's so small down here, letter H. Top right-hand corner, letter H. It is hydrogen. Just like we have an alphabet, and our alphabet, we kind of have an order to it, right? We go A, B, C, D, E, F, G. Well, our periodic table is also arranged in kind of an order, and it's numerical. In the top corner right there, can you guys see how there's number 1? That is known as hydrogen's atomic number. It is number 1. What was that? Oh, actually not quite. Okay, so number 1. Yeah, 1 is right here, but you make a good point. 3 and 4 are right here, so they do kind of go in order, but number 2 is over here. So this is the first thing I need to teach you, is that when you read the table, you're always going like you do in reading, like from left to right. So 1 is here, 2 is way over here. Later today, I'm going to explain why the heck we put 2 way over there. But for right now, I just need you to know it goes 1, then 2. Then back to the next line, 3 and 4. But then when you want to look for number 5, there's a big gap. 5, 6, 7, 8, 9, and 10 are right there. And then kind of like with reading, it starts over again. 11, 12, big gap, 13. So again, in a little while, I'll try to explain why there's that big gap in the middle, because there's a reason for it. But at least for right now, does this make sense as to how to read this? So it goes in order of number. 1, way over here 2. 3, 4. Skip a bunch. 5, 6, 7. Kale. Kind of. There's some logic to that. Yep. I will get to that if that's okay, guys. I'm going to try to do this like sequentially. There is opposites of each other here. I need to point something out then. There are 2 rows that are buried down here at the bottom. You see how there's 2 rows on your table that are way at the bottom down there? Okay. Now, this table right here, I think does a good job as any to try to explain it. If you look at the numbering system, it goes, I'm just going to try to write it out here. I'm stealing yours. This one goes 55, right about here. See that one there, 55? Then it goes 56. Then it goes 57. And then it skips to 72, which is confusing because it's like, where the heck did the rest of them go? That's what I'm trying to explain right now. Right here, between 50, oh, no, not right there. Undo that. Go ahead, undo. There we go. Right here, between the 57 and the 72, there's even a black line on your table. You guys see that black line? That black line implies that 57, 58, 59, 60, and all the way are down here. And what we've done is we've saved space. Okay? The table should actually have all of those elements in one big massive row. It would actually go 55, 56, 57, and then all of those ones, I'm going to have to go back here, I think, actually, just for you guys to see this. Sorry, you have to turn around and watch me. What it means is that these guys right here, what should have happened on the table is that all of these elements right here should have been shoved into here. And it would have made the table really long. Does that make sense at all? But to save some space, it's almost like we cut them out, and we literally cut out all of these elements, and we just put them down below, just to save room. Otherwise, it would be like forever across. Yeah. It's to save space. Yeah, well, further on in chemistry, there actually was a good reason why they chose those ones, because we could have chosen any elements to kind of cut out and save space. So we actually purposely chose these ones, but for right now, that's basically the rationale. So what I need you guys to know then for our table is there's actually not 9 rows. Some people think that there are 9 rows. They go, there's 1, 2, 3, 4, 5, 6, 7, 8, 9. They say there's 9 rows in this table. There's not. There's actually 7 rows. There's 1, 2, 3, 4, 5. 6 really goes like this. Dun, 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 dun. Keep going. And row 7 goes like this. Dun, 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 and keep going. Okay. So there's actually not 9 rows on your table. There's 7. And they go in order of number. Right? So it just basically goes 1, 2, 3, 4, 5, 6, 7. Right? And what do we call that number? It's called the atomic number. Does that make sense so far? So let's do just kind of a practice guessing game to kind of get used to learning our letters. Just like I would do with my daughter, where I might give her a flashcard, why don't I give you guys a little challenge? Okay. I'm going to ask you to find me atomic number. Let's go with 4, 28, and 72, and just tell me who they are. All right, so just find it on your data booklet, and let's just do this kind of as a practice guessing game. Who is number 4? Just yell it out, guys. Beryllium. Yeah, number 4 is beryllium. 28 looks like it is Ni, nickel. 72 is hafnium. Yeah, so there we go. So hopefully you're able to kind of follow along here. Grab your periodic table. You're going to want it out pretty much all unit, by the way, okay? Like this periodic table that I've given you here, you're going to want it for the rest of our units. So make sure it's nearby. Don't lose it. I'll give you a new one if you do, but... Okay. So if I were to ask you to like number them in order, that's how it works. Okay. Now, many of these things, rather than writing out the full name, we give them a symbol. For example, beryllium is Be, or nickel is Ni, or hafnium was HF. And like most of them make sense. Because like the first 2 letters of beryllium is Be, right? And the first 2 letters of nickel is Ni. And then like hafnium, it's like, well, this H and this F. That kind of makes sense, right? But there's some letters, there's some that like make no sense at all. Yeah, let's do that one, mercury. What number is mercury, Clayton? Number 80. So try to find number 80. Mercury is number 80, and it is Hg. Yeah, gold is also weird. Iron. Okay, so many of the ones that have like letters that don't match up, I need you guys to know that often they are based on like say Latin names. Okay. For example, Clayton, you brought up Mercury. I don't actually know the Latin name for Mercury, but I do know a different one. Iron is Fe, and Fe, iron, is number 26 if you can find it. And so although we call it iron, its Latin name is ferrous. And so ferrous is where they got the Fe from for iron. Sometimes I think it's because they ran out of like the English letters, because sometimes they would have overlapped. You'd have had like two that were the same. But for the most part, many of them are like H is hydrogen. He is helium, right? So, but yeah, some of them have a weird one. Okay, let's talk a bit about these elements for a bit. So they're organized by number. Okay, we call that the atomic number. There are actually a few different ways we can categorize our elements. And this is what Mendeleev did when he did his first periodic table. He tried to group things together. Okay. Your periodic table has some different colors. Ideally, this would have been in color, but it's not in color. I'm sorry. Like maybe you can see the shading a little bit. So hopefully this one or other pictures that are in color will help you. So here's how we can break things down. Here's the first one. We can figure out whether it's considered to be naturally occurring or synthetic. I want to discuss that for a bit. Naturally occurring would be something that like I could go and like find somewhere on Earth, like in a mine, or I could like find it occurring somewhere and I could go collect it myself. Okay. For example, like gold. Gold is naturally occurring on Earth because I can go and find gold in a gold mine and I can mine it. Or nitrogen. Nitrogen, we breathe in nitrogen. It's like most of our atmosphere. Most of the elements are things that are naturally occurring. But there are some things that we don't actually like find on Earth. And we have to like synthesize in a lab. And one of the weird things about things that are synthetic is that many of them do not last long. Like they have like a short lifespan. That's a good word to use for now. And eventually they like turn into something else. Many of these things are radioactive. What I need to do is show you guys how to tell whether something is naturally occurring or synthetic. Because that is something I need you to know, is to be able to identify what are the things that are naturally found on Earth and which are the ones that we have to like make in a lab. Okay. Here's how you tell. I want you to find a couple of different elements here. I'm just going to compare. Try to find number 8. 8 should be oxygen. Can you guys find that one? And I want you to compare 8, which is oxygen, to number, where is it? 43, which is technetium. Really funny word. Can you guys find the two of these guys right here? Okay, I want to point out a number that's also on this square. We're not ready to use this number yet. It's actually in the top corner. Oxygen is 16.00. Can you guys find how oxygen has 16.00 in the top corner? That is an indicator that this is naturally occurring. Naturally occurring. Now, I don't know that I can explain why it is based on that number, but can you guys just accept, for at least for right now, as I'm teaching you from the basics here, that this number is naturally occurring. But I want you to go compare to technetium. Technetium, number 43, has 98, but more importantly, it is in a bracket. Okay, that bracket is how we can tell whether something is synthetic. Synthetic. So anything that's got a little bracket around it is synthetic. So if you guys can, look around the table and try to find some other ones that have brackets on them. You'll notice that many of them, if you're looking at your periodic table, many of the synthetic ones are like down here in the bottom corner, and many of them are also in like those extra 2 rows. You know those extra 2 rows that are down there? Many of the synthetic ones are down there, but that's not all of them. Okay. So how do you tell if something is synthetic? It's got those, I mean, look, I even put a little bracket around radioactive here. That's how you can tell. If it's got a little bracket around this number right here, it's synthetic. Later, much in the future, later I will tell you what those numbers mean. But does that make sense for now? Okay. So There are about 90 naturally occurring elements and 25 synthetic ones. There is even a spot on your table, not yours, but can we look at the one in the back here? For elements that scientists are trying to make currently. Can you guys see how a lot of these ones right here, they even have the radioactive symbol on them? Can you guys see that right there? A little white and the yellow and black symbol. You might notice that this table right here stops number 111, Rogengeni. I don't even know what it's called. Is that where your table stops, number 111? But you guys might notice that this table keeps going. There's actually another one here, and there's more right here. Your table's probably fairly old because science has progressed in the last decade, and so scientists are working on trying to make these elements here and create them. Now, some of these last ones here are actually left with like UU as the front letters. That's because like we haven't even named it yet because it hasn't been discovered, but when it gets discovered, we're going to give it a name. But like for right now, this is just a placeholder. So they just call it UUT, UUQ, UQP, UUH, and so this is just like what we expect to one day get discovered. I have to double check on this one, but I think that Copernicum, number 112, is probably something that has been discovered, but it's not on your table, but this one is newer than yours. Does that make sense? And maybe one day, number 113, it'll have a name. And if I discover it, it'll be called Schalkium. Right? Or you name it after yourself, right? Does that make sense? So the table is actually something that we expect to keep building as scientists discover how to synthetically make new compounds and make new elements. Yeah, yeah, exactly. Yeah. What's the metal in Wakanda for that? Vibranium, yeah. Which, granted, is like a pretend one, right? But okay, here's some more properties I need you guys to know. On your table is something called, stay with me, guys, something called a staircase line. I don't want to tell you where the staircase line is, but can you guys look at your table and find something that would logically be a staircase line? Yeah. Yeah, you guys, some of you are finding it here. Let me go back here. So there are two bolded sections. There's a bold section right about here, which I've already discussed. The other is right about here. There's a staircase. You can't see that. Let me change the color. This right here is called the staircase line. And it's been arbitrarily kind of drawn in there because it's what helps separate what are known as our metals and our nonmetals. Okay? There are like three categories. I've actually got them listed on the next few slides. There are metals, and you guys will be familiar with most metals. Metals are things like copper, zinc, gold and silver, lead. Okay? If it is a metal, you guys are pretty familiar with it. Okay? And here are some properties of metals. They're usually strong. They're usually quite durable. We previously talked about these words, malleability and ductility, right? Malleability, you can bend it into a sheet of something. It's flexible. Ductility, you can braid it into a wire. These things are also usually hard, good conductors of heat and electricity. So everything that is on this side of the table over here, these are known as our metals. There's a lot of metals, yep. Even those ones down there, those would be considered part of our metals, most likely. Yep. Now, what's the opposite of a metal? A non-metal. And so over here on this side of the table are what we call our non-metals. And they basically have the opposite properties. They are not conductors. They are not strong. They are not ductile. You might actually notice if this was in better color, you would actually notice that many of these things are liquids or gases. I know your table that I gave you isn't in color. I'm sorry. We don't have a color printer this big. But like most of these things over here, these guys are solids. And these guys over here are gases or liquids because they're not made of metal. There's a third category, however. They're called the metalloids. And our metalloids are kind of like the in-between ones, where they kind of are like metals and they're kind of like non-metals. They're kind of in between, hence metalloids. And they are the things that are basically on the top and bottom of the staircase. You guys will notice that this staircase right here, I know I've drawn all over it, but this staircase right here, with one exception, this element right here, if it's on the top or the bottom of the staircase and it touches like the sides of it, it's called a metalloid. The one exception is this guy in this spot right here, and that is aluminum. And most people will know that aluminum's not a metalloid because they know aluminum's metal. But like, if I go to my slide up here that talks about it, boron, silicon, germanium, arsenic, antimony, tellurium, polonium, and astatine, these are all known as metalloids because they're both. They're like both metal and non-metal. They kind of have like some of both properties. Almost everything else, though, is basically in like one half or the other. So there's a second thing I need you guys to be able to do. If I gave you a random element, I could ask you, tell me whether it is natural or synthetic. And another thing I might ask you to do is if I gave you a random element, I might ask you to tell me whether it is a metal, a non-metal, or a metalloid. Does that make sense? So let's play a little game here. Because again, this is like me quizzing my 4-year-old. I want you guys to try to find number 48, cadmium. Number 48, cadmium. Is it a metal or a non-metal or a metalloid? It's a metal because it's on that side of the table. And is it natural or synthetic? Perfect. Okay, let's try another one here. Try to find me number 53, iodide. 53, iodide. It is a non-metal, and it is naturally occurring. Okay. One last one. I just got to look for an interesting one to try here. Try to find number 87 called francium. 87 called francium. It is a metal, but it is synthetic because it's actually highly radioactive, and it is probably only going to occur in a lab setting where we have to like make it. Clayton. No, good question. So there are actually, yeah, it is actually considered to be a metal, although its natural state is actually liquid. I haven't talked about that, but there's the states of matter. And again, you guys can't overly see it well on your table, but can you see how mercury number 80 has like a bit of a shading to it? The reason why number 80 is shaded a bit is because it's still a metal, but it's actually liquid. How do we convert things from solid liquid to gas? Yeah, heat. Okay. So metalloids are not based on temperature. Metalloids are based on properties. So you know how you mentioned a second ago that like mercury is kind of like a liquidy kind of thing there? But if I want to make it a solid, I just have to make it colder. Does that make sense? So a metalloid doesn't mean that it's like, you get what I'm saying here? A metalloid doesn't mean that it's like a somewhat melted solid. That's not the definition of a metalloid. It means its properties are like kind of halfway in between of what metals and nonmetals have. Okay, next topic of conversation. We need to discuss something known as the groups. Okay. When Mendeleev decided to make his first periodic table, he actually put things together in 18 groups. Okay. And he combined things together based on like some similarities. These are now the 18 columns in your table. I'm going to go stand at the back of the class again if you guys don't mind, just because I want you to see a periodic table. This right here, an up and down row, is known as a group. So this is known as group 1. This one in yellow is known as group 2. This would be group 3, group 4, group 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And like, can you guys see at the top of your table? It literally gives you like a big chart there, like very, very, very top of the page. It gives you numbers from 1 to 18, like in boxes. Okay. Those are the 18 groups. Okay. We call them families. It's another name for them. We call them families. Why do we call them families? This is the most important thing I need you guys to like memorize. They have similar chemical properties. Mendeleev decided that when he made his grid, there are like 100 elements. He could have made it 10 by 10. He could have made it 11 by 9. He could have made it 14 by 7. You get what I'm saying here? But he chose 18 as how many groups there was. Because 18 to him logically was like how many different like families had similar properties. Okay. Now, I can't fully explain this until I teach you more, but I want to show you a commonality that might help you understand this. Can you guys find group 1? Okay. Group 1 is going to involve these elements. Hydrogen, which is number 1. Then below that is lithium, which is number 3. Below lithium is potassium, which is number 11. You're right, sodium's in bananas. Potassium's in bananas, it's number 19. Can you guys find in that row there something that is the same for every single element there? What is the same in our first like column. Yeah. Now we're not ready to talk about what the 1 plus means just yet. We got to do this in like steps. But can you guys see that each one of these elements has a +1 charge on it? And hopefully you guys will notice some patterns here. In group 2, everybody in the second row has a +2 charge, doesn't they? Okay, hydrogen actually has some exceptions to it as well, but minus hydrogen also having a -1. Would you guys agree, though, that everybody in group 1 has +1s? Okay. So what has been discovered, give me one sec here. What Mendeleev discovered is that things that reacted similarly, he put them together in up and down rows. So if you look at the third row of the table, row 3 has scandium, it's +3. Below scandium is yttrium. Why? It is also +3. Below that is lanthium. And guess what? La is also +3. Does that make sense? Seabass. Good question. Okay. This is actually, we may as well write this down now since he asked. This particular periodic table does not list all of the charges. Now, we're not going to use charges yet. We're not that far yet. But yeah, Seabass noticed that if you look at the far side of the table, so let me just draw a really rough table. It looks something like this. You have like that. There's one up there, and a few over. Okay. So Seabass noticed that everything over here, they don't have charges. So we can actually write some of them in if you'd like. Everybody in the very, very, very last group right here, this is group 18, it actually has 0 charge. It actually is neutral. So if you want to write that above, everybody in group 18 has no charge. And I don't know why this particular table doesn't put a charge on there, because if you found a different periodic table online, it might even tell you it's 0. Everybody in group 17, the second last group, they all have a charge of -1. And someone earlier today, I think Clayton, it might have been you, mentioned that like they're on opposite sides of the table for something. Those charges are actually something we're going to talk about later, because things on this side of the table are usually positive, and things on this side of the table are usually negative. Again, we're not ready for that yet. We'll build to that. Let's do one more. Everything in group 16 actually has a -2 charge. Yeah. And if you wanted to keep going, everything in group 15 would be -3. There's kind of a pattern to this. Now, for whatever reason, this table doesn't write them in, so if you want to write them above, feel free. Like I said, we're not going to use this yet, but we will eventually talk about what those charges mean. But for now, what I need you guys to know is Mendeleev chose 18 rows because he found 18 different, like, similar groupings, and he put them on top of each other, and charge is one of the best ways for us to figure that out. While you're writing that down, some of them even have special names. So I would write this down on your table. Group 1, we call them the alkali metals. So if you'd like to write this down right above the first group, we call them alkalis. Again, they all react very similarly to each other. These are all +1. And if you look on the periodic table, with a few exceptions, because there are exceptions here and there, there's pretty much no other +1s anywhere else, other than in this row. Group 2, they're all +2, and we call them the alkaline earth metals. And again, although there are some exceptions, for the most part, everything that's +2 went in this column. Then if you want to skip to the opposite side of the table, group 17 has a name called the halogens. And we had already written this down. The halogens all have a -1 charge. And again, if you were looking for anything else that had a -1 charge, it would have to be in that column. There are no other -1s other than in that column of 17s there. The last one, the noble gases or inert gases, I want to pause and talk about this one for a bit. These guys had 0 charge, or like not applicable charge. There's actually a reason why we call them this. I don't know what you guys have learned in social studies before, but have you ever taken like a topic where they talk about like kings and serfs and having a fiefdom? Are any of those words familiar? If you can imagine that like it's 500 years ago and there's like the nobility, you could be like a baron or a duke, or you can be a peasant, those sorts of terms. If you were a noble person, you had a title. You were a king or a duchess or a duke or something like that. If you were noble, if you were nobility, you did not hang out with commoners. Does that make sense? Like the nobility, they like stuck their noses in the air and like they only hung out with other nobility. They were very exclusive. Because of that, that's actually why we call this last group the noble gases, because they have zero charge. And zero charge means that they cannot form compounds. When we eventually talk about compounds, because they have zero charge to them, they stay by themselves. And because of that, we call them noble. Now, a better word for this in chemistry is inert. Inert basically means non-reactive, if you want to write that down. Inert means non-reactive. And so everything that is in the last column does not react with anything else. It likes to stay by itself as an element. And again, like when I'm teaching you guys this sort of stuff, I want to use the analogy of me teaching Cami how to read. Sometimes we have to do things in like chunks. For example, the next thing I got to teach my daughter Cami is like what the sounds the letters make. Like for example, A makes A, and B is B, and C is K. But there are some weird exceptions. For example, the letter G. G can make a J sound or a G sound. Now, when I'm first teaching Cami how to read, though, I kind of like have to like not pick words that have that in it because it's confusing. You get what I'm saying? I don't teach my daughter about silent letters, and she hasn't learned about how like PH makes an F sound. You get what I'm saying here? That's going to happen a lot as I teach you chemistry. Have to like, we'll get to it later. You're not ready for it yet. Does that make sense? So I'll do my best to describe it, but if this whole inert noble gas thing having zero charge, that didn't make sense to you, that's fine. Like we're not there yet. Okay. But anyways, those are our groups. Okay. Then periods are next. Periods are basically the rows across. And what I need to point out is that there are only 7 rows. There are not 9. I've already discussed this though, right? There are 7 rows, not 9. Because these 2 rows down here actually slot in right there. It just saves some space. Okay. Now what I need you guys to know about periods is that these all share what is known as an energy level. We discussed this briefly when we talked about a guy named Bohr. We're going to talk about this more later as it comes up. Again, I got to do this in like bite-sized chunks. But if you can just write this down for now, each one of these new rows is a new energy level. Did I discuss with you guys the idea of electrons literally like hopping from like one orbit to another? We talked about that a bit, the teleporting idea? Okay. If that helps for right now, think of each of these rows as being like a new orbital. Remember this sort of picture here? Let me draw one real quick. The picture of like there's a nucleus, and then there's electrons going around in circles, and we know they don't actually go in circles. But like if it helps to picture it, each one of these new rings is like an energy level, and electrons can literally hop from this one to that one to this one, and you would never ever find one in between. Okay, so if that helps, each one of these rows is like a new level, so to speak. If you're playing like Super Mario Brothers, or whatever video game you're talking about, we're at a new level. So every time you have a new level, you got to go down a row. Sound good? Okay. Okay, so I want to talk a bit about these atoms then that we're discussing. Now that we've discussed a bit about the periodic table, we should discuss what is in these atoms. One of the stories I would have told you back when it was like story time with Chris Day, where we went through a bunch of scientists, we'd have talked about a guy named Ernest Rutherford. And Ernest Rutherford did an experiment where he shot particles at gold, and they phased right through it, which he thought was the weirdest thing in the world. Because normally if I like punch the wall, my hand doesn't go through it. And stuff went right through it. And he hypothesized that our matter looks more like this. It looks more like this idea here, where there's a whole bunch of stuff in the middle, and the electrons are around it. And if you had another atom, a second one, it would also have these sorts of levels to it. And if I tried to put something through it, it could actually phase right through. Now, why does my hand not go through the wall? Because my hand is much bigger. Does that make sense? But if you had like small particles, they could actually phase right through or possibly bounce off. He didn't expect them to deflect, but once in a while they would. What I want to do right now then is discuss this nucleus. Okay. In the nucleus, there are two things, neutrons and protons. And maybe you've heard those words before, but if not, I want to let you know how they work. A neutron is a small particle that has no charge to it. Neutrons are neutral. They have no charge to them. Protons are positive. And so in the nucleus, you have a picture that looks like this one right here, where if you can kind of envision it, you got all these little subatomic particles inside here. And some of them don't add any charge to it, and some of them give you some positives. That's what's in our nucleus. And these nucleus, or nuclei if you have lots of them, they are very, very small, like tiny. Okay. What surrounds the nucleus? The electrons. Because if you have positive stuff, you better also have negative stuff. And so the positives are in this nucleus, but these little dots right here, those are our electrons. And we know that our electrons are negative. So we now have three different types of what we call the subatomic particles. And the reason why they're called subatomic is that they are smaller than atoms. This is what our atoms are made of. We would have talked about a guy named John Dalton. And Dalton had this idea that matter was indivisible. That's actually where the word atom came from. I don't know if you guys recall this, but atomos is Greek for atom, and it means indivisible. And they thought that you couldn't cut it in half. We've actually since discovered, no, there's smaller pieces to it. So I need you to know the three pieces: neutrons, protons, and electrons. Okay. Now, here's kind of a slide that kind of summarizes this. What I need you guys to know is that we may draw a diagram that looks like this. This is a good pictorial diagram. We call this a Bohr diagram, if it ever comes up. And the reason why we call it a Bohr diagram is that it kind of shows electrons in these rings. Okay. Now, the first thing I need you guys to know about these atoms is that atoms are neutral. So if atoms are neutral, you better have protons equaling electrons. Okay. Like for example, if you have 8 protons and you have 9 electrons, is this something that is neutral? No. Because like imagine there was a big fight. You bring 8 protons to a fight, and you bring 9 electrons to a fight. Right? Okay, well this guy takes that one, and these 4 take those 4, and these 3 take these 3. There's one left over, right? So if it is an atom, it needs to be exactly the same, your protons and electrons. Okay. Now, how do you know how many protons something has? This is really important. Your protons are based on your atomic number. Now, I started class by talking about this. The atomic number is the number that's up in the top corner, like there. Hydrogen is number 1. Or, for example, oxygen is number 8. So you know how I talked about how we put them in order of number? But that number is not random. That number is how many protons they have. So let's play another little game here. How many protons does aluminum have? Find aluminum on your table and tell me how many protons it has. Aluminum. There. Aluminum is number 13, so aluminum has 13 protons. Okay, let's try another game. Tell me how many protons potassium has. It's going to take you a little while to find potassium. Woo, fast. Potassium is K, it's number 19. So if you want to figure out how many protons something has, look at its atomic number. But we can extend this game. If we're talking about an atom, they're neutral, so protons equals electrons. So what that means is if I asked you how many electrons hydrogen has, it has 1 electron and 1 proton. Or if I asked you how many electrons oxygen has, it also has 8. So really, the way these things work is that as they get further up the table, they get bigger. Why do they get bigger? Because each new number adds 1 more proton and 1 more electron. Does that make sense? Hydrogen has 1 proton and 1 electron. Helium has 2 and 2. Lithium has 3 and 3. Oxygen has 8 and 8. And cadmium has 48 and 48. Does that make sense? And what we've discovered is that there's kind of a pattern to how the electrons work, though. Remember, in the nucleus is where you find your protons, but the electrons kind of go in these rings around the outside. There's a bit of a pattern to it. And this pattern explains why the table has the shape it does. The first energy level, watch me at the back here, guys. The first energy level has 2 electrons in it. Why does the first energy level have 2 electrons? Because there's 1, 2 in the first row. Then it's full. As soon as you fill the first ring, you have to move to the next ring. The next ring has 1, 2, 3, 4, 5, 6, 7, 8. As soon as you fill that ring, you need another ring. The next ring also has 8. 1, 2, 3, 4, 5, 6, 7, 8. Can you guys look at the pictures that I have right here in this slide? How many electrons are in the first ring of both molecules, or both atoms? 2, right? Here's the first ring. It has 2 electrons. Here's the first ring. It has 2 electrons. The reason why is that on our periodic table, the first row at the top has 1 hydrogen, 1 helium. There's room for 2. I like to think of this like a motel, I guess, or maybe a hotel. The first floor has 2 rooms in it. As soon as the first floor is filled, you got to go to the second floor. How many rooms does the second floor have? Up to 8. Up to 8. You have to memorize this. It is the same for everything, yeah. So the first row always holds 2. The second and third rows always hold 8, and then 18. So I want to try to explain this picture right here. Oxygen right here, if I were to draw a picture of it, oxygen is number 8, which means it has 8 protons and it has 8 electrons. But the question is, where do we find those 8 electrons? Okay. Well, the first floor can have 2. Well, then how many can the second floor have? Up to 8, but it only uses 6, because there's 1, 2, 3, 4, 5, 6, 7, 8. See how oxygen does have 8 electrons? But where we find them is 2 on the first floor and 6 on the second floor. 2 plus 1, 2, 3, 4, 5, 6 gives you 8. What that means then is that oxygen's floor right here, this second ring, there's actually room for more. It can have at most 8. As soon as you hit 8, you start a new ring. Like look at magnesium. Magnesium is number 12. If it has 12 protons, it better have 12 electrons. Just quick count with me. Are there 12 electrons here? 2, 4, 6, 8, 10, 12. You guys agree there's 12 electrons there? But the where we find them is based on this pattern. The first ring has 2 electrons. The second ring can have up to 8 electrons. And as soon as the second ring gets filled, you have to open up the next ring, which can also hold 8 electrons. Now, unlike oxygen, which only used 6 out of its 8 right here, magnesium uses up its full row right here, which explains why magnesium is in a different row than oxygen. Can you guys see how oxygen is in the second row? It needs 2 rings around it. But magnesium is in the third row, 1, 2, 3, third row down, because it needs to have the first ring, the second ring, and then it needs a third one even. Does that make sense at all? So this is what we're going to try to work on and build towards, because it's going to take a while to really sink in. But magnesium is number 12, so it should have 12 electrons, 2 in the first ring, 8 in the second ring, and then 2 and 8 makes 10, right? We need 12, so there's 2 more in the last one. Let's try another example here, and then I'll answer your question if I could. Let's try one more. Let's try to figure out how do the electrons work. How do electrons work on, let's try aluminum. Okay. So here's how we're going to solve this problem. First, we have to figure out what number aluminum is. Aluminum is number 13. Okay, so here's what that means. It has 13 protons, and it has 13 electrons. Now, where are all the protons found? In the nucleus. So if I were to draw the picture, I can kind of like start with a core in the middle and say there's 13 protons here. Sometimes I will write P plus for protons, by the way, and I'll write E minus for electrons. So there are 13 protons all shoved into that nucleus. Now I'm going to draw my first electron level. how full can this level get? 2. That's the pattern, 2. So I'm going to put 2 electrons in the first ring. And now this is now full. Which explains, why is there 2? Because the first level has 1, 2, and then it's filled up. So how many electrons can fit in the second row? 1, 2, 3, 4, 5, 6, 7, 8. So your second, ring, so to speak, has a capacity of 8. So if I were to draw another ring here, I would draw 1, 2, 3, 4, 5, 6, 7, 8. How many electrons have I used total now? 10. But how many do I need? Okay. So first level holds 2. Second level holds 8. 2 and 8 is 10. But I need 13. How many more do I need? 3. So I'm going to open up my third level. Now again, this third level can house as many as 8. I don't need to use all 8. I just need to draw 3 in the last ring. And this is called a Bohr diagram. Should we try one more? Because this is one of the most fundamental skills we got to work on. Let's try another one. How many? No, I want to keep it simple. That's going to be tricky. How many electrons? I shouldn't say how many. I should say where do electrons in, let's say, potassium go? Where do the electrons in potassium go? So first thing we got to do, we got to find where potassium is on our table. Potassium is number 19, which means it has 19 protons and 19 electrons. So first I'm going to draw a nucleus. And in the nucleus, I'm not going to draw 19 of these, but imagine that somewhere in the nucleus here, I have drawn 19 protons. Well, around the nucleus is where we find the electrons. And the pattern is always the same. The first, level, so to speak, has 2 electrons in it. 1, 2. Why is there 2? Well, that's how many elements are in the first row on your table. It kind of explains why there's that big gap in the middle. Then the next row. How many electrons can fit in row 2? 8. Okay, so I'm going to do a running total. We're at 2. This would make it 3, 4, 5, 6, 7, 8, 9, 10. But I need 19. I'm not even there yet. I had 2. I added 8. I'm up to 10, but I need more. So I'm going to open up another level. This level also has a capacity of 8. How do I know its capacity is 8? Yeah, look at row 3. How many across does row 3 have? Well, 2 and then 6 more for 8. Okay, so I was at 10. This will make it 11, 12, 13, 14, 15, 16, 17, 18. I added 8 more. I'm up to 18. I need 19, right? So 19 means I need to open up one more level. Almost running out of room here even. Can I make that go away? One more level. And this last level has 1 electron. Does that make sense? Yeah. And you're ahead of me here. Let's fast forward here. Where's that picture? There's a picture in our notes here, actually. There's a picture in our notes here that kind of shows some of these diagrams here. And what I want to do right now is mention some similarities in these diagrams. Can you guys find this one that's way ahead here? What you guys might notice is that everybody in group 1, remember how everybody in group 1 was a +1 charge? I can actually explain to you a bit better now why they all have a +1 charge. Everybody in this row has something in common. The last ring has 1 electron in it. Look, the only ring here has 1 electron in it. Here we've got the row of 2, but then the outside ring has 1 electron. Check out this guy here. There's a ring here, there's a ring here, but look in the last ring. See how there's only 1 electron? There's some similarities. Check out the next guy. We said these guys were +2. The reason these guys are +2 is look at their electrons. There's 2 electrons in the last ring. And here there are 2 electrons in the last ring. There's a lot of similarities here. Okay. Now, I did kind of skip ahead, but that would be an example. These are called Bohr diagrams, and they're going to be helpful later on when we try to make compounds out of things. But for right now, I want to kind of skip back if that's okay. I'm not going to finish my notes today because I have quite a bit more to get to. So I kind of knew this was going to be a two-part lesson. So why don't I try to finish off with this thing here on atomic number and mass number, and then we're going to call her a day. So let me go back to this. It's going to take a while for this to sink in, okay? So don't stress if you're like, "Ooh, I don't get this yet." We're working up, okay? So we've now talked about the three different types of subatomic particles. There are protons and neutrons found in the nucleus, and there are electrons found in orbitals. And these are their charges. Positive for proton, neutral for neutron, negative for electron. Okay. The last thing we want to talk about here is, this is my slide here, is something called the atomic number, the mass number, and whether it's an atom or an ion. Okay. The atomic number is the number that's like on your table that tells you like what number it is. Like for example, hydrogen is number 1. Helium is number 2. It tells you how many protons you have. What I want to discuss next is something called an isotope. Now, an isotope is how heavy it is. Okay. I want to give you an example here. These are both carbon. And the reason why they're both carbon is that they both have 6 red inside. Can you guys see how there's 1, 2, 3, 4, 5, 6? And this one over here, there's 1, 2, 3, 4, 5, 6. They both have 6 red. Red means they have 6 protons. However, these ones right here have 6 of the white inside. Guys, stay with me. I know it's been a long lesson. I'm sorry it's a long day of me talking, but try to stay with me. Can you guys see how this one right here has 6 white, but there's 8 white over here? Those are neutrons. Neutrons are neutral, and you can have more neutrons and not change what it is. This guy right here is called a carbon-12. We would call this carbon-12. And this one right here is called a carbon-14. Here's how that works. Carbon has to have 6 protons. Why does it have to have 6 protons? Well, because carbon is number 6. Okay. I guarantee you carbon has 6 protons. Otherwise, it's called something entirely different. But depending on how many neutrons it has, guys, stay with me, okay? I'm not getting your best attention. I know it's been a long day, but this is important stuff, okay? Try to give me your best attention here. The number that's associated with it here is how many protons plus neutrons you have. That is called a mass number. Protons plus neutrons is called a mass number. And so if I tell you that you have carbon-12, it means it weighs 12. If I tell you that you have carbon-14, it means it weighs 14. The only difference is that there's more neutrons. I want to say this again because this is super important. I cannot add more protons. Because if you add more protons, you call it something else. For example, if there's 6 protons, call it carbon. If there's 7 protons, it's the next number. But you know what you can mess around with? Neutrons. You can have more of them. And that's called a mass number. Okay. So I want to show you some examples of some mass numbers. This guy right here is called a hydrogen 1. Here's how it works. See how the bottom number is always number 1? It's because hydrogen is number 1. This is also a 1, and this is also a 1 because hydrogen is number 1. It has 1 proton. But the top number tells you how heavy it is, its mass. Now, the top number is basically add your protons and neutrons to each other. So if the top number is number 1, there is 1 proton, no neutrons, because 1 and 0 adds to 1. Well, let's say the top number is number 2. How many protons does it have to have? 1, because it's hydrogen. But if it has a 2 at the top, it means there's 1 proton, 1 neutron, because 1 and 1 adds up to 2. And let's say I give you a 3 and a 1 up here. The bottom number for 1 means there's 1 proton, so it makes it hydrogen. But if there's a 3 up top, there are 2 neutrons. Here's how this works basically. If you want to figure out how many neutrons something has, you take these 2 numbers here and you subtract them. I'm going to try some examples, and then we're going to call it a day because it's been a long lesson. Let's say I gave you this random element. I don't even know what it is, so I'm going to use a question mark. Okay. And let's say I told you that the bottom number down here was 13, and the top number was 20. Let's try a guessing game here. This is like my daughter, Cammie. You guys are learning your letters. It's okay if you don't get it yet. We got to do some practice on this. my first question is like, what is this element if it's got a question mark in the corner here? Well, we start with the bottom number right here. Can you guys find me number 13 on your table? Who is number 13? Okay, so this is no longer a mystery anymore. Because of that 13, I now know this guy is aluminum. And so aluminum must have 13 protons. That's what makes it aluminum. How many electrons does it have? 13. Because we've learned that atoms have electrons and protons the same. The last question I want to ask you, though, is how many neutrons does it have? And the answer is 7. If I tell you the answer is 7, maybe you can kind of try to figure out where I got the 7 from. If not, here's the logic. Protons and neutrons add to give this number right here. 13 plus 7 gives you 20. Let me try a few more examples. You guys can kind of start to pack up a little bit if you want. But this is what we're going to build on tomorrow. No, this would have been, it's protons that defines what it is. It would have been aluminum. Let me try a couple more here. Get packed up, but then let me finish the class until I run out of time with this. I'm going to give a couple of question mark ones here. And we'll try these together as a class. So I'm going to try a couple last examples here with you guys as we wrap up. Okay, so pack up, I guess, but watch as I do this, okay? Here's how we would solve a puzzle like this. Again, you don't need to get this right yet, okay? This is like my daughter learning how to read. This is a long-term process. We're building skills here. Here's a skill I hope you guys have learned today. Yeah. Yep. Yeah, so let's start with that. Clayton, how did you know that this was magnesium? Perfect, yeah. So look up number 12 on the periodic table. 12 is magnesium, so now I know what it is. What's that? You cannot. Good question. You cannot have half of something. So here's how we would write this. Magnesium has 12 protons. That's what makes it magnesium. It will have 12 electrons. But if I asked you how many neutrons this has, it would have had 7. Oh, sorry, neutrons. Neutrons would have been 7. Because 7 plus 12 makes 19. So protons is always this bottom number, though, right? So let's try this one here. Who is number 7 on the table? Nitrogen. It is no longer a mystery to me anymore. I now know this is nitrogen. Because it's nitrogen, it has 7 protons, and it has 7 electrons. The question, though, is how many neutrons does it have? And the answer here is also 7. Because this 7 and this 7 add up to give 14. Now, some kids ask, Chris, why don't we care about the electrons? Great question. Where do we find the electrons, though? Are they in the nucleus? No. We only care about stuff in the nucleus. Okay? So only protons and neutrons matters. Last one, then we're going. Number 32. Is that copper? What's 32? Nope. It is germanium. So I know who this is now based on the bottom number. The bottom number of number 32 tells me that this is germanium, which means it has 32 protons and it has 32 electrons. But if I want to know how many neutrons it has, it depends on this number here. The answer was 28. How did I get 28? 32 and 28, when you add those numbers, give 60. Okay, a couple thoughts, then we can take off. Guys, I need to thank you. This was a long lesson. I kind of tried to warn you in advance. This is like the building blocks of chemistry. I'm going to finish this tomorrow, and then we've got to spend some time practicing this. Okay? If you don't get this immediately, that's fine. Okay? But we're going to work on this, okay? Okay, thanks, guys. Have a great Wednesday. We'll see you tomorrow, and we'll continue this.